Welcome student to the class of Polymer blends and alloys. I am Archana Misra. Now today's topic of discussion is significance of polymer blends and alloys. Actually, blending may improve resin or product performance. That is by producing materials having a full set of the desired properties at a lowest cost, and also that is also extending the engineering resin performance by incorporation of less expensive polymers, and that will also improve the specific properties that are shown here. First, the brittleness. The toughening of brittle polymers thus eliminated the need to use low molecular weight additives. So, plasticizer in the flexible PVC formulation. So, if we want to take a toughened polymer or polymer blends, then there is no need to add plasticizer. By adding only the elastomer polymer, we will get a toughened polymer blends. And modulus and dimensional stability is also improved by blending with more rigid and more heat resistance resin. Improvement in solvent and chemical resistance is obtained by the incorporation of semi-crystalline polymer into an amorphous resin, that is the blends of polycarbonate with polyester resin, and improving the flame resistance properties by incorporation of non-flammable resin into a flammable one. For example, styrenics or acrylics with PVC. Now, permanently anti-static properties are also improved by blending with polymers having either OH or SH functionality, that is ethylene oxide, co-epichlorohydrin with ABS PC blends. And biodegradability is also improved by incorporation of a biodegradable resin. So, blending makes it possible to produce integrated multi-layer structure, and that will also providing means for recycling of industrial or municipal plastics blend. So, the blending technology makes it possible to rebuild high molecular weights of partially degraded polymers, thus to produce high performance articles from plastic waste. So, blending may also lead to improved processability. The process the high TZ resin at temperature well below the thermal degradation temperature. That is only possible by the incorporation of a miscible resin with a lower glass transition temperature. For example, PS PP blends, and reduce pressure drop across the dies or runners, thereby increasing productivity. That is possible by incorporation of an immiscible low viscosity resin. For example, liquid crystal polymers or polyether ether blends. Blending also have a controllable degree of strain hardening. Blending with resins that either by itself show high strain hardening. For example, LDP in blends with another PO, or when reactivity blended forms long chain branches. For example, polystyrene in blends with polyphenylene oxide. These materials show better processability in technologies where the external flow field is important. For example, film blowing, blow molding, wire coating, foaming, etc. And to stabilize the foaming process, that is possible by the incorporation of elastomeric particles that will improve the nucleation of gas bubbles, and hence it stabilizes the foaming process, and that will also reduces bubble size and the final foam density. And blending also provides the means for generation of a controllable amount of the foaming gas during the ensuing stages of processing, for example injection molding. That will be possible only by the incorporation of a degradable resin into an engineering or specialty one. Easier, more stable processing is possible by blending with different grades of the same resin, broaden the molecular weight distribution, which in turn results in easier, more stable processing, as well as better mechanical performance. Blending also improves product uniformity, that means scrap reduction and plant economy. Blending ascertains quick formulation changes, thus plant flexibility and productivity. Blending also reduces the number of grades that need to be manufactured and stored. So, blending technology offers method for producing higher aesthetic values materials. For example, film or coating without gel particle or face size, molding with stick-free surface finish, etc. There are also the advantages or reasons for blending. That is to extend engineering resin performance by diluting it with low cost commodity and pertinence polymer, and to develop materials with a full set of desired properties, to utilize the scrap generated at various steps. Sometimes blending is also done to develop a recyclable material, for example, using starch as a second component. That is also used to get a high performance blend from synergistically interacting polymers, and that is also used to achieve customer specification in a product and to reduce R&D expenses and the time consumed in developing new monomers and polymers to yield a similar property profile, and also lower capital expansion involved with set scale up and commercialization. So, this is all about the significance or advantages or reasons for blending. Thank you.